Okay, so we had these two different K expressions. Now there is going to be a relationship between those two that we're going to have to know. Like if you have a Kc given to you, you may have a problem that says, well, what is the Kp value? Or you may have to do something with a Kc, but you're given Kp. So we'll need to be able to convert between those two. I want to show you how we come up with the relationship between Kc and Kp. A little derivation to start us off for a week. And as usual, this derivation is going to become real messy real fast, but then we'll clean it up and it'll look nice at the end. They always do. So we begin this derivation with our good old friend, the ideal gas law, PV equals nRT. And with that, because we're talking about gases, pressures of gases, now we can even, if I can take it back here for a second, these are all gases. There's nothing dissolved in water in this case, yet I still give you an expression of concentrations. Well, how can a gas have a concentration? It turns out that a gas can have a concentration. If we talk about how many moles of a gas are present in 1 liter of a gas, not 1 liter of solution, which is weird because we're always talking about solutions for concentration. But you can have a molarity of a gas, moles of gas per liter. And the higher the pressure, the higher the concentration, because you'll be cramming more particles into that liter. So, if we take this ideal gas law and rearrange it, and we divide out the volume, so it's only pressure on the left, and the volume, this is the same thing as nRT over V. We've talked about this before, how multiplication and division does not matter what order you do them in. So if I just take moles over volume times RT, that's the same thing as nRT over volume. Is it not? Is it? It is. Or if I took 1 over V times nRT, it's the same thing. You're going to get the same thing every time. You can put numbers in and try it if you want to. But I kind of selected n over V as my thing that's going to divide the V. Why? What do you get when you take n divided by V? N is moles, right? And V is volume, which is in liters because R has liters in it. So with the ideal gas law, this V's got to be liters. Moles over liters. That would be the molarity. Yes? So I'm going to just solve this thing for molarity. That's molarity, and then divide out the RT. So the molarity is P, and I have it right here. Molarity is P over RT. For a gas, for an ideal gas. I'll use that definition of molarity on the next page. Oh, wait a second. Okay. Now on the next page, we're going to try to relate Kc to Kp. So, and I'll just put it up here so we're reminded. The chemical equation we have is nitrogen gas plus 3 hydrogens yields to an equilibrium with 2 NH3 gases. And so from that we have this expression for Kc, products over reactants. Coefficients became powers. And we found from the last slide that the molarity of a gas is equal to pressure over RT. So, those are molarities. So we can just make a substitution. We can call this pressure of ammonia, NH3, over RT. That's the molarity, and that got squared. See how that was squared? And in the, that's just the numerator. The denominator has the N2, which is the pressure of N2 over RT. That's just the first power, times the pressure of H2 over RT. That got cubed. So this is Kc. That's all that would be equal to Kc. Now notice that I specified what gas I have with the pressure. I didn't make any specification for R and T. Well, R is an ideal gas constant. It doesn't matter what substance you're talking about. R is always the same. And the temperature, take a look at this. This is a container in which there's reactants and products both present. That's what happens at equilibrium. Everything is in the same container. So they all have to have the same temperature. So I didn't specify anything for the temperature either, because they're all the same. So, but the pressures are not all the same. So if I just make a little separation here, the P's are variables, so I'll put the P's, like consider them at once and all the RT's at once. Take a look at how the RT's are arranged. How would the RT's shake out? What would we end up with? We have an RT quantity squared here, and an RT quantity to the fourth power here. Notice that was cubed, so cubed times another RT. So we got RT to the fourth here, and RT squared there. And how does that simplify? Can you tell? What do you do with something that's in the denominator of the denominator? It goes up to the top, doesn't it? Yeah, it does. And that's because when you divide fractions, which is what we're doing here, you take the numerator and you multiply by the reciprocal of the denominator. Well, the reciprocal of the denominator means that whatever's in the bottom of the denominator becomes the numerator. That's right. Yes. So we're going to wind up with RT to the fourth over RT squared for the RT terms. And that would be RT to the second power. Are you with me on that? It's right. Yeah. Now, what else do we have? We're left with now the pressure of NH3 squared over the pressure of N2 times the pressure of H2 cubed. Now, what do you see inside of the big parentheses? That's Kp. Right, that's Kp. Yep, the pressure of the product divided by the pressure of the reactant. Oh, this is the Kp or expression. So, that thing right there is Kp. Now, one other thing. How do you think I came up with that 2? Where did that 2 come from? I had RT squared over here, RT to the fourth down here. How do I know what the exponent on the RTs are going to be, or what it is going to be? Where did that 2 come from? From what?
RT to the fourth divided by RT squared is RT.
Yeah, so where did the 2 and the 4 come from? From the coefficients in the equation, yes. From the coefficients. If anybody said it before, I just didn't hear you. Now, let's say, how do we get a 2 out of the coefficients? It looks like it's reactant coefficients minus products, doesn't it? Is that where it came from? Yes, it is. All right, now reactants minus products. We never do reactants minus products. It's always products minus reactants, isn't it? So here's what I'm going to call it. I'm going to call this RT. And if I called it delta N, the delta always means final minus initial. So it would be 2 minus 4. But this one was 4 minus 2. So is it okay if I call it negative delta N? That would be the reactants minus the products. N for gas. The N is just like what the coefficients are. And that's being multiplied by Kp. So my RT is raised to the negative delta N power, and this term right here is just Kp. All right, now this thing right here, if you have a negative power, that means that it should be Kp divided by RT to the delta N, right? Negative power means it goes into the denominator. So it's going to look like this, Kp over RT quantity to the delta N. Positive delta N, because I now stuck it in the denominator. Yes? And I did all of that so that we can now clean this thing up Now RT to the delta N power is in the denominator. If I just took that term that's in the denominator and moved it over to the other side of the equation, the other side of the equation is just Kc. That's how I get this. Kp, there it is by itself because I moved the RT over, equals Kc times RT to the delta N power. That's the relationship between those two Ks. Kp and Kc are related like this. I have to do that derivation, otherwise if I just gave it to you, you'd think, well, how'd you get that? Well, now you don't have to think that. Now, a couple things about this one. And be careful with this because our brains are now pretty much conditioned. When we see the R term, because we've had all this thermochemistry stuff, we think automatically 8.31. But remember, R is only automatically 8.31 if it's in an equation that involves energy. There's no energy here. It's just like the point in a chemical reaction. So it turns out that Kp is always the ratio of the pressures in atmospheres. And you might want to write that down for yourself because I never wrote it anywhere else. Kp, you must use the pressures in atmospheres and find their ratio. If you don't use atmospheres, it's not going to be right. Actually, coincidentally, once in a while it might be right. But in general, that's not the way to do it. So if Kp is in atmospheres, then we're going to use this value for R, 0.0821. This is the R value when your pressure is in atmospheres with the ideal gas law. So that's going to be one you're going to want to try to remember. I mean, I'll give you the value of R, but you'll also have 8.31 given to you because some of our other problems use 8.31, so know which one to use. I think I mentioned this the other day too, but I wanted to say it again just to make sure that I did. The K value will never have a unit. Even if when you're taking products divided by reactants, even if the units don't cancel out, K does not get a unit, ever. Did I tell you that before? I was thinking that I did, but it's worth repeating. Yep, K is unitless, even if the units of what you're calculating don't cancel. You still leave the unit off. K is strictly a ratio. One last thing about this equation. I need a memory trick to remember where the P and the C go. Because if I don't have some trick to remember, then when I came back to this a week later, I wouldn't remember if the C was there or there. Is it Kc equals Kp times RT, or is it Kp equals Kc? I don't remember. So this is dumb. And when I tell you the way I remember, you're going to think to yourself, that guy's really stupid. But it helps me remember. I think of this as the politically correct equation. It's nothing to do with politics at all, or political correctness. But I remember the P comes before the C in that expression, so that's the way I remember it. And I had somebody else before that told me, well, think of the royal family. Prince Charles, his father's name was Philip. So Philip came before Charles. So I'm not into the royal family at all. I would have never thought of that. But that's another thing. Or if there's something else meaningful to you, and maybe you're just very good at remembering things, which I'm not. But yeah, the P comes before the C in there. So let's see if we can use that. I'm going to take you to one of the problems in our handout. If you take that handout out. Go to number 10. Do you need an extra copy?
No, I just have it.
You what?
I have it.
Oh, well, I have it actually. Number 10 makes me smile the way the question is written too. Consider the hydrogen shift reaction. That is amusing to me because when I look at the chemical equation, to me it's an oxygen shift because oxygen leaves the water and goes to the CO.
but they didn't ask me to name it.